First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Okay, in this video, we're going to look at Riemann sums, practice problems. In this video, we're just going to work out some example problems and just kind of work through them. During the process, there may be some things we do, and you may wonder, well, why are we doing this? I will refer you back to the video on the conceptual foundation. So we're not going to elaborate much on this particular video. We're just going to kind of work problems out. We do recommend you looking at the conceptual foundations video first if you don't have the conceptual foundation for Riemann sums. So in this particular video, we're just going to get straight to the Riemann sums. And this is the part 1 video where we'll look exclusively at, finding Riemann sums, looking at functions. And in the part 2 video, we'll take more of a look at Riemann sums from looking at tables. All right, let's get it. All right, so here is our first problem. And the good thing about Riemann sum problems, the good thing about them compared to a lot of different other type of problems you'll see in calculus is when it's a Riemann sums problem, they're pretty much going to tell you it's a Riemann sum problem. And they're going to tell you whether it's going to be a left Riemann sum or a right Riemann sum or a midpoint Riemann sum. Or they may say, finding the area under the curve using rectangles with right endpoints or left endpoints, or the midpoint of the rectangle hitting a function. So, a lot of times in calculus, a big dilemma is what type of problem is this? Is this related rates? Is this optimizations? Is this chain rule? Is this product rule? You have no such worries for Riemann sum problems. So that's the good news. And so once you have the process down, these are very easy problems to digest. So I'm going to go ahead and read the problem and just go ahead and solve it. So it says let f be the function given by f of x is 100 to the power of x. If 4 subintervals of equal length are used, what is the value of the right Riemann sum approximation for the integral from 0 to 2 of f of x? Now, one thing I will elaborate on, again, on these problems, we're doing 2 types of videos for our concepts now. One goes over the conceptual foundation, which is important. And then the other videos, we're just practicing problems. And we split it up just so the videos won't be as long. But here is something that wasn't really touched on in the conceptual foundation. So I'm going to touch on this just a little bit. And that is the fact that a Riemann sum is an approximation of area under the curve, which is an approximation of a definite integral. And this is a definite integral. And we talk about the area going from the integral from a to b. Well, that a and that b are the limits of this definite integral, or the numbers you see on this integral. So for our particular problem, a is going to be 0 and b is going to be 2. So when you see this integral notation, if you're not familiar with it, in terms of what we've been talking about thus far with Riemann sums, this is just the interval in which we're finding area under the curve, if you will. All right, let's go ahead and get into the problem. All right, so those are the particulars of the problem that you see written down there. And anytime I do a Riemann sum problem, the first thing I want to find is the value of delta x. And delta x is b minus a over n. So for this particular problem, that's 2 minus 0 over 4, which is 2 over 4, or 1/2. So the first thing we find is delta x. And again, if there are any questions, what does delta x even mean? Again, refer back to the video on the conceptual foundations of the Riemann sum. So after we find delta x, we're going to find the numbers of our subintervals, and we're going to start with the value of a. And what we're going to do is just add delta x until we get to b. So we start with 0, so I'm going to add 1/2, and I get 1/2, and I add 1/2 again, and I get 1, and I add 1/2 again, I get 3 over 2, and I add 1/2 again, and I get 2. So it's kind of like an arithmetic sequence, if you will, where your common difference is the value of delta x. Now, when you have your numbers of your subintervals, you're going to evaluate the function at each of those numbers except for one, and depending on if it's a left or right Riemann sum, which one you're not going to use. So when you're doing a right Riemann sum, you're going to use every number except for the first number. So I'm going to use all of these numbers. And once again, if you don't understand why, refer back to the conceptual foundation video. So this video is assuming you have those conceptual foundations And you should be clear why I'm using every number except for the first number. So therefore, this Riemann sum, which in this problem was written as the integral from 0 to 2 of f of x dx. And so this is an approximation. And the approximation will be f evaluated at these values, and those are like the length or the height of the rectangle, times delta x, which is the width of each rectangle. So f of 1/2 times 1/2, f of 1 times 1/2, f of 3/2 times 1/2, and lastly, f of 2 times 1/2. And so from there, we're just, we have to figure out the value of f of 1/2 and f of 1, etc., and just plug it in and do the arithmetic. You'll notice on all these problems when, delta x, when the rectangles or the subintervals are equally spaced, then of course the width of each rectangle is the same for each particular product. And in many cases, we can factor that out. Sometimes it's advantageous to do so. And sometimes maybe it's best to keep it like this, but I'm going to go ahead and follow the practice of factoring it out. So I'm just going to rewrite this statement with the 1/2 factored out. So this integral from 0 to 2 of f of x would be 1/2 times f of 1/2 plus f of 1 plus f of 3/2 plus f of 2. All right, so we're just going to figure out what those values are. Now, again, remember f of x is 100 to the power of x. So when I'm finding f of 1/2, for instance, I'm just going to raise 100 to the power of 1/2. All right, so let's do that. So 1/2. So 100 to the power of 1/2 is 10. 100 to the power of 1 is 100. 100 to the power of 3/2. Now, when you raise a number to a rational exponent, the numerator of that exponent is the power and the denominator is the root. So you have to take a power and a root, order of your choice. It doesn't really matter. I prefer to take the root first because it'll make the number smaller and then take the power. So I'm going to take the second root of 100, which is 10, and then raise 10 to the third power, which will be 1,000. And then something you can also note for this particular problem, since it's going up by 1/2 each time, and 1/2 is an exponent for 100, and 100 to the 1/2 power is 10, you should notice that these numbers are just increasing by multiples of 10 each time, kind of like a geometric series where r is 10. So we can just assume that this next number is going to be 10,000, and I'll go through the well, this is just 100 to the second power, and so it's going to have 4 zeros, and you see 4 zeros there. So that's pretty much it. Now to do the arithmetic in this case, so I would prefer to half all of these individually versus adding this up and then halving. I think that's the easier way for this particular problem. So if I half these, I get 5 plus 50 plus 500 plus 5,000, and means our answer would be 5,555. So that's our first example. And just to recap, the things we like to do, we want to find the value of delta x first. After we find the value of delta x, we're going to write the numbers of our subintervals. We're going to begin with A and keep adding delta x until we get to B. And if we do a right Riemann sum, we're going to evaluate the function at every value except for the first value and sum those up times delta x. And if we're doing a left Riemann sum, as we'll do in our next example, we're going to use every number in the subintervals except for the last number, and then we'll sum those up times delta x. All right, so this one we got 5,555. All right, so that was the answer we received. Let's look at the next one we want to look at. Okay, this next example is worded a little differently, but no matter how it's worded, again, if we have that strong conceptual understanding of what a Riemann sum represents, then we'll still be able to do the problem effectively. So this one says find the approximate area between a curve f of x, and you see what f of x is, and the x-axis on the interval 0 to 12 using 4 rectangles. Use the left endpoint of each rectangle to determine the height. So this is a left Riemann sum. A is 0, B is 12, N is 4. Let's get it. All right, so there's the problem there. Again, the first thing we want to do is find the value of delta x. So delta x would be 12 minus 0 over 4, or 12 over 4, or 3. After we find delta x, we want to find the numbers of our subintervals. So we'll start with A, which is 0, and we'll just keep adding delta x until we get to B. So 0, 3, 6, 9, 12. All right, and this is a left Riemann sum. So we're going to evaluate the function at every value except for the last value. So I'm going to evaluate the function at those values. So when I do a left Riemann sum, I don't use the last number. When I do a right Riemann sum, I don't use the first number. So this one is just an approximation of the area. So this area will approximately be, and I'm going to take the value of delta x, which is 3, and then that would be times f of 0 plus f of 3 plus f of 6 plus f of 9. All right, so I just need to figure out what those values are. And so I'm going to calculate those values separately real quick and then plug them in. It's a little bit of arithmetic for some of them. So let's see, I'm doing 0, 3, 6, and 9. So I just want to see the function there to reference. And so let me find f of 0, which is the easiest one to find. F of 0 would just be 2. Everything with x will become 0. Next, I'll find f of 3. So f of 3 is negative 2 times 3 squared. That's negative 18. And then 3 times 24 is 72. So that's 54 right there, plus 2 is 56. And let's find f of 6. So f of 6 is negative 2 times 6 squared. That's negative 2 times 36. That's negative 72. And then 6 times 24 is 144. So that's positive 72 right there. And so positive 72 plus 2 is 74. And now, lastly, let's find f of 9. So f of 9, so that's negative 2 times 9 squared. 9 squared is 81 times negative 2 is negative 162. Plus 9 times 24. 9 times 20 is 180. And 9 times 4 is 36. So that's 216. That's 216. So that's 54 right there, plus 2, 56. All right, so those are the values for f of 0, 3, 6, and 9. So we'll just plug those in to the expression and do the arithmetic. All right. So we have 3 times, so f of 0 was 2, and f of 3 was 56, and f of 6 was 74, and f of 9 was 56. All right, so let's see the easiest way to do this arithmetic. And I think it would be good to add those two numbers together first. That's 130. And these two are 58. So 130 and 58 would be 188. So this is 3 times 188. And 3 times 180 is 540. And 3 times 8 is 24. So I have 540 and 24. So that's 564. All right, so that's the second example. We'll do one more example in this part 1 video of Riemann sum practice problems. Okay, so on this one, we got 564. All right, our next problem, let f be the function given by f of x equals sine x. If 6 subintervals are equal length are used, what is the value of the right Riemann sum approximation for the integral from 0 to pi of f of x? Okay, so in this problem, we got 6 subintervals, so n is 6. And from the integral sign, we can see a is 0 and b is pi. All right, let's take a look at this one. All right, so you know what's first? Delta x. Delta x here is going to be pi minus 0 over 6 or pi over 6. Now we'll find the values of our subintervals. We'll start with 0 and just keep adding pi over 6 until we get to b, until we get to pi. So 0 plus pi over 6 would be pi over 6. And then pi over 6 plus pi over 6 will be pi over 3. And then pi over 3 plus pi over 6 will be pi over 2. And then pi over 2 plus pi over 6 would be 2 pi over 3. And then 2 pi over 3 plus pi over 6 would be 5 pi over 6. And then 5 pi over 6 plus pi over 6 would be pi. 1, 2, 3, 4, 5, 6, 7. All right, so those are our 7 numbers. That gives us our 6 subintervals, and this is a right Riemann sum. So we're going to be utilizing every number except for the first number. So these are the values that we're going to evaluate the function at. Now the function is just sine x. And you know, for values like pi over 6 and pi over 3 and pi over 2 and pi, those should be very straightforward. You know, sometimes these two, there's a little thinking involved. However, since pi is positive in quadrants 1 and 2, meaning pi is positive from 0 to pi, we don't have to worry about the sign. So, you know, sometimes dealing with unit circle trigonometry, you know, when you get a value that's greater than pi over 2, you have to think about the sign, positive or negative, of the trig value. Well, for sine in quadrants 1 and 2, sine is positive. So that's not something we don't have to worry about. So that's pretty good news. But as you'll see in many things you do in calculus, it's very important to know your unit circle trig and know your trig values, particularly, you know, the trigonometric values for pi over 6, pi over 3, and pi over 4, and every angle that has one of those as a reference angle, and also of the quadrantal angles. And then also understanding when you have an angle with a reference angle of one of our 3 main angles in a different quadrant, how to determine if that's going to be positive or negative. Those are all things that are very important for the calculus student. But let's go ahead and digest this problem. So this one, we're approximating the integral from 0 to pi of f of x dx, and that's going to be pi over 6 times f of x evaluated at these values. So pi over 6 times f of pi over 6 plus f of pi over 3 plus f of pi over 2 plus f of 2 pi over 3 plus f of 5 pi over 6 and plus f of pi. All right. So you got 6 subintervals, so you know it's going to be 6 little calculations that you have to do. Okay, so let's figure this stuff out. And I put an equal sign here. You know, technically this is an approximation. All right. So let's see. So the integral from 0 to pi of f of x dx, you know, is approximately, by this method, the following. All right, so pi over 6 times. All right, so f of pi over 6 is sine of pi over 6. Sine of pi over 6 is 1/2. Sine of pi over 3 is the square root of 3 over 2. Sine of pi over 2 is 1. So those were nice and easy. Now the next one is the sine of 2 pi over 3. Well, 2 pi over 3 has a reference angle of pi over 3, and sine is positive in quadrant 2. So it's going to be the same thing as the sine of pi over 3. And so that's going to be the square root of 3 over 2. And the sine of 5 pi over 6, okay, 5 pi over 6 has a reference angle of pi over 6. So that's going to be the same thing as the sine of pi over 6, which is 1/2. And then sine of pi is 0. So I don't have to write 0. So these are my values here. So I'll add stuff that should be added together. For instance, I can combine 1/2 and 1/2 to get 1, which will combine with this 1 and equal 2. So this is pi over 6 times 2. And then I have the square root of 3 over 2 plus the square root of 3 over 2. And that's just going to be the square root of 3. And that's my answer. You know, if you're doing multiple choice problems, you know, depending on who makes the problems, perhaps they might distribute this pi over 6. The way this problem was made, and I made this problem, I chose not to distribute the pi over 6. So the answer should be left like that. So that concludes part 1 of Riemann sum practice problems. Again, these we're dealing mainly with functions. Come back to part 2, and we'll look at it with tables. And also in this video, we looked only at left and right Riemann sums. And in part 2, we'll also take a look at midpoint Riemann sums. We'll see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.